Well, welcome back. I am snuck back into the school to make more videos for you guys. Hopefully my computer will be fixed and the internet's working at my house. Had some issues there, but now I can sneak into the campus and try to make videos for you guys. So here is section 5.3, the structure of f adjoined x modded out by p of x when p of x is irreducible. Again, we're looking for the structure, what kind of ring we're going to have. And we have here Theorem 5.10 says this: let f be a field and p of x a non-constant polynomial in f adjoined x. Then the following statements are equivalent. The famous T, F, A. The following are equivalent. Number one, p of x is an irreducible polynomial. P of x is irreducible in f adjoined x. Number two, f adjoined x modded out by p of x is a field. And number three, f adjoined x modded out by p of x is an integral domain. Now, a couple of things here. You may be looking at this going, what? That doesn't make any sense. Yeah, it actually does. So let me explain. Remember, irreducible polynomials are prime-ish. You can't call them prime, but they act like primes. And remember, when we took z mod n and we modded out by a prime, we always got a field. So when you take a polynomial ring modded out by an irreducible polynomial, being irreducible is prime-ish, you're going to get the same result. You're going to get a field. So p of x is irreducible means my f adjoined x modded out by p of x, also known as a quotient ring later on, is a field. So this f adjoined x modded out by p of x is a field means you have p of x must have been irreducible. The following are equivalent. Well, you got this third statement down here, and I'll put a little star by it. It says this: f adjoined x modded out by p of x is an integral domain. Well, duh. The fact is, if you got a field, automatically got an integral domain. The definition of a field is an integral domain with all non-zero elements or units. But sometimes you want to sit there and you want to look at these fields as integral domains. What's an integral domain? It's a commutative ring with identity with no zero divisors. So if you focus on the lack of zero divisors, you're focusing on the integral domain part of the field. But in this world, the other deal is this: when you got f adjoined x modded out by p of x, and you have a commutative ring with identity and no zero divisors, you got an integral domain, but don't worry, you're also, all the non-zero elements are going to end up being units as well, so you end up getting a field. So integral domains and fields are going to be the same thing in this world, because fields are integral domains, but when you got it, when this type of ring is an integral domain, it automatically becomes a field. It's even stronger. You'll have a field. So we won't call these guys integral domains. So that's kind of the emphasis Dr. Hungerford is actually going for. So here's the big question here. So I'll give you an example. Try to give myself an easy one here. Z2 adjoined x modded out by the polynomial x squared plus x plus 1. Well, what kind of ring is it? So I'll give you the list. Is it a basic ring? Is it a commutative ring? Is it a ring with identity? Is it a commutative ring with identity? Is it an integral domain, or is it going to be a field? Well, the fact of the matter is, because we're doing these equivalence classes in Z2 adjoined x, we know this ring is going to, the elements of this ring are going to look like, this is a degree 2 polynomial, so when you mod out by a degree 2 polynomial, you're going to end up getting degree 1 or less. So degree 1 or less would be the famous ax plus b, where the a and the b come from Z2. That's where my field is joined at. So I got Z2, you got choices of 0 and 1. So you got two choices for A, and 0, 1, two choices for B. So I got 2 by 2, that's 4. There's 4 actual equivalence classes here. And you could draw out the multiplication table if you really, really wanted to, but you don't need to. All we need to do is figure out what kind of polynomial this guy is. Because in this world of Z2 adjoined x, because Z2 is commutable, it has the identity 1, so you have the, in the polynomial ring, you have 1 times x, which is going to be in here. So you don't have to worry about ever being a basic ring. Yes, it's a commutative ring, and it's a ring with identity, so you can get rid of this mess, because it's going to be either a commutative ring with identity, an integral domain, or a field. Well, we know, thanks to this theorem up here, The integral domains and fields are the same thing, because when you get an integral domain, actually all the non-zero elements end up being units, so you might as well call it a field. So don't call it an integral domain, so knock that out. So there's really only two options with this world. It's either going to be a commutative ring with identity, or it's going to be a field. Now you got to figure out which one. Well, you figure it out by, is this polynomial, p of x equals x squared plus x plus 1, is it irreducible or not? Well, how do I figure out if it's irreducible? Well, from the last section, we're going to look for the roots or the zeros from section 5.2. So with Z2, all I got to worry about are the equivalence classes of 0 and 1. Let's see if any of these guys are going to give me 0. Is it going to be a root? 0, x-intercept, however you want to call it. Typically, we call these guys roots or zeros. So plug in 0, that's easy. That would be 0 squared plus 0 plus 1, plugging in 0 for x. And that gives me 1, which is not the 0 equivalence class. So, not a root there. So now I'm going to plug in 1. 1 squared plus 1 plus 1. And 1 squared is 1 plus 1 plus 1 is 3. So this will be the equivalence class 3, but we are in Z2 adjoined x, so 3 is equivalent to, subtract off 2, is equivalent to 1, but you don't get 0 again, so not equal to 0. So we got 1 and 1 again, so no roots. So my polynomial does not have roots in the Z2, which means that the p of x, which is equal to x squared plus x plus 1, is irreducible, because you had no roots, irreducible in the ring of Z adjoined x, which makes Z2 adjoined x modded out by the x squared plus x plus 1. What kind of ring? This is going to be a field. If I actually had a root, it will be a reducible polynomial. And the reducible polynomial would not be part of this theorem, which means there's only one option it can be. If you actually were mod out by a polynomial that was reducible, not irreducible, you end up getting commutative ring with identity. So there's only two options, but this is showing your work. And I didn't have to go very deep into showing my work, and I didn't have to do the multiplication table of the Z2 adjoined x modded out by x squared plus x plus 1 with the quotient, with the equivalence classes being ax plus b. So, some ideas behind here, setting you up for future math classes and the like. You have Theorem 5.11 says this: let f be a field, and p of x an irreducible polynomial in f adjoined x. Then f adjoined x modded out by p of x is going to be an extension field of f that contains a root of p of x. Now what this means is this. So we've got this idea of an extension field. So I have to write you guys a note, or pretty much as a definition. So the word definition here. If f is a field, and f is a subfield of another field k. So we're talking about a world of fields. So you got fields inside of fields. You have the big field, and inside of that you have f, but it's also a field, so you have a subfield of another field. K is on the outside, f's on the inside. So f is actually contained inside of k. Then k is called a field extension of f. So here's your field, and you extend it some more to create another field. So in terms of future math classes, the 4,000 and 5,000, the senior and graduate level classes, f is called a field or a subfield, it depends on which way you look at it, of a field k. But if you focus on the field k, field f, k is actually called an overfield or over ring. It's a ring, it's above the other ring. So you would call this an overfield actually, because k is a field, but you also have this idea of over rings. So it depends on what your focus is. If your focus is on the inside, that's f is the field, then k would be called an overfield. Okay, but if your focus is k on the outside, then f is called the, that's a subfield. And so another word for overfield is a field extension. So k is a field extension of f. So you extended this field to another field. So in this world, see, in f adjoined x modded out by p of x, this actually contains the field f, because you got your let a be equal to 0 and your b be 1 on the ax plus b mod. You'll get all the elements of your field. So your field will always be contained inside of your f adjoint x modded out by p of x polynomial. So your field is always contained inside of this guy, and when this guy you mod out by an irreducible polynomial, we know this is a field, so you've got a field contained inside of another field, and that's what we're seeing here. And it also, if you play around with it, the f will actually contain a root of this particular polynomial when you start playing around with this guy. So there's this idea of the isomorphisms and the like, so we'll talk a little bit more about that, but not much. So, by theorem 5.8 and 5.10, such that f is a field and p of x is an irreducible polynomial in f adjoint x, then f adjoint x modded out by p of x is an extension field of f. This is your big K guy. Your field that where all the coefficients come from is actually going to be contained inside of this. So here is your f is your focus on your field. F adjoint x modded out by p of x is this field extension. That's what this main idea of this theorem 5.11 is. And it also is going to contain, this field will actually contain a root of that particular polynomial p of x. Well, p of x is irreducible. True, but it's an overfield. It's not, the polynomial doesn't, f adjoint x doesn't have the root in it, but this field does. So corollary, describe it a little bit more, corollary 5.12 says this: let f be a field and f of x a non-constant polynomial in f adjoint x. Then there is an extension field K of f that contains a root of f of x. So if we just talk about it in general, being f of x, all right, f is contained inside of f adjoint x modded out by f of x. It could be irreducible or reducible. We don't care. This guy may be a field or it may not be. It may be just a commutative ring with identity. Well, you can extend this guy, add some more elements on there, and you can create this idea of K. So this guy, depends on what f is, it can be contained inside of a K. And if f is irreducible, then these two guys are equal to each other. And there's an isomorphism to a field that you may be familiar with. You know, if you look at the example they gave you in the book, they make the field extension the complex numbers. It doesn't look like the complex numbers, but it's isomorphic to the complex numbers, so it's pretty much the same thing. So again, if you look at the information below the proof of corollary 5.12, they try to explain this by showing you an isomorphism from this stuff. So is this stuff overly important? No. It will be in, like I said, in the graduate level, senior level classes, we'll go back and take a look at these ideas of field extensions of what's going on here, but you keep building bigger and bigger. So that goes back to that original question, how many rings out there are there? There's an infinite amount, and you can keep creating these idea of rings. And typically they're going to be isomorphic to something that you're typically familiar with, but there's lots of rings out there. So what was real important from section 5. And section 5.3 is honestly, it was theorem 5.10. This is a whole section about one theorem. The relationship between, you know, your congruence class f adjoint x modded out by p of x. When p of x is irreducible, your f adjoint x modded out by p of x is a field. If f adjoint x modded out by some polynomial happens to be a field, that polynomial is irreducible in f adjoint x. So it kind of goes both ways. This is the main idea. So how would we actually kind of word that on a particular problem? Here is a problem for you guys. So just to kind of give you a hint of what kind of questions I can give you, here's one. Part one of this thing, it's a two-parter here, so I'll call this part A, and yep, they're down there if you look way down deep. There's a part B here, but we'll get that in a second. Part A says this: find all the equivalence classes of Z3 adjoint x modded out by 2x squared plus 2x plus 1. Well, all the equivalence classes. The first thing I do is I look at that, first off, what field I'm attached to. This is Z3. We're modding out by a prime, so this is a field. Adjoint x, polynomial ring, coefficients come from field, modded out by the polynomial 2x squared plus 2x plus 1. So that's my f of x, which is 2x squared plus 2x plus 1. Now, what are the equivalence classes going to look like? Well, what you should have learned from section 5.1 and 5.2 is the equivalence classes are the remainder when you divide by this f of x, this 2x squared plus 2x plus 1, and focus on degrees. If you divide by an x squared polynomial, your remainders have to be a degree less than that. Degree less than 2 is a degree 1, which means it's linear. If famous ax plus b. So if you're modding out by a cubic polynomial, x cubed, then this would have been ax squared plus bx plus c. It would look quadratic. It's always a degree less, 1 degree less. So where you've got ax plus b as equivalence classes, where a and b are elements of Z3. So I got 3 choices for A and 3 choices for B. Grand total, there are 9 equivalence classes, 3 times 3. It didn't ask me how many, it asked me to write them out. So to write them out, you've got to catch a pattern on this thing. So I'm going to write these guys out in the form of ax plus b, where A and B come from Z3. Remind you, the elements of Z3 are equivalence class 0, equivalence class 1, and equivalence class 2. So what I do here is basically set myself up a chart for A and B. I'm going to start off with A being equal to 0, and I'll run the gamut on the B's. So here's my first column of these guys. So A is 0, B could be 0, so that would be just the 0 equivalence class. A is 0, B could be 1, and A is 0, B could be 2. 0, 1, 2. And that actually is the field Z3. It's contained inside the equivalence class, like we talked about before. But now, I'm going to move up, I'm going to let A equal 1, and then run the gamut on B. If A is 1, I end up getting x plus 0. A is 1, I get x plus 1. And then A is 0, A is 1, I get x plus B could be 2. Run the gamut on B. 0, 1, and 2 for B. X is always 1. So I get equivalence class x, equivalence class x plus 1, and equivalence class x plus 2. So the next one I'm going to let A equal 2, and then run the gauntlet of B, all the things that B can be. So A is 2, so I can get 2x, and then B would be 0, that would give me 2x. I give 2x, then B could be 1, that would be 2x plus 1, and then B could be 2, that would give me 2x plus 2. So A is 0, run the gauntlet of B. A is 1, run the gauntlet on B. A is 2, run the gauntlet on B. And I systematically do this. And I know how many I need. 3 choices for A, 3 choices for B, multiplication principle, 3 times 3 is 9. And notice 1, 2, 3, 4, 5, 6, 7, 8, 9. I have all the equivalence classes. Now, what kind of ring is it? Well, we now know that when I take a field, slide up here, you guys see this, field adjoined x, modded out by any kind of polynomial f of x, this congruence class is going to be either, it's going to be a field, or it's going to be a commutative ring with identity. Those are my 2 options. And how do I know? It depends on if f of x is irreducible or if f of x is reducible. So we got to focus on f of x. In this example, f of x was 2x squared plus 2x plus 1. So f of x is equal to 2x squared plus 2x plus 1. And what I'm going to do to see if it's reducible or irreducible from previous chapters, all I got to do is look for roots. But these are finite fields. So I'm talking about Z2 adjoined x modded out by this 2x squared plus 2x plus 1. So that's my polynomial, 2x squared plus 2x plus 1. In Z2, all I've got to do is check 0, 1, and 2. And to be a 0, I got to get 0. So honestly, I'm going to cheat on this thing. And I'm going to actually graph this polynomial in my calculator. So here we go. And here is what the polynomial looks like. So you guys can see it. And I'm doing this just so I can plug in numbers. Now, okay, I can plug in 0 real easy and I get 1. But second, calculate value on my calculator, number 1 there. I hit enter. X was equal to 0, and it gives me 1. And that is in Z2, so 1 is the equivalence class 1, but it's not 0, so don't care about it. Now I'm going to plug in second calculate value at 1, and I end up getting 5. But 5 is beyond Z2, so sorry, Z3 here, Z3. So 5 is beyond 3, so I'm going to subtract multiples of 3, and I get 2. This is equal to 2, but more importantly, it's not 0. So we're in Z3 adjoined X here. So my choices are 0, 1, and 2 here. So, and then I'm going to plug in 2. So I plug in 2 into my guy, and I get 13. 13, again, is beyond the scope of Z3. So I'll either divide by 3, see what the remainder is, or I can just keep subtracting on 3 until I get a number between 0 and 2. So if I subtract off 3 enough, it goes into 12. I think I'm left with 1 left over, but it's not 0. So what this tells me is I've got no roots. And if I've got no roots, that means f of x is irreducible. These are the words I want to see, which means therefore, 3 dots in a triangular fashion means therefore, my equivalence class ring, my Z3 adjoined x modded out by 2x squared plus 2x plus 1 is a field by Theorem 5.10. If I had a root, just plug it in and show that somebody was equal to 0, then I would say this polynomial is irreducible, and then my other option would have been, it would have been a commutative ring with identity. Those are the only 2 options for my congruence class rings I get with polynomial rings modded out by a certain polynomial, f adjoint x modded out by p of x look to it. So I got another one over here. So what kind of ring is this one? I didn't ask how many elements are in there. My question is, what kind of ring is it? So all I did was change the field. This is Z5 adjoined x modded out by 2x squared plus 2x plus 1. Same polynomial, but my field is different. Now it is Z5, okay? So, how many, we know that the equivalence class is going to look like AX plus B, but now A and B come from Z5. Z5, 0, 1, 2, 3, 4. I have 5 choices for A, 5 choices for B. That's a grand total of 25 equivalence classes. 25 elements make up this particular ring, but what kind of ring is it going to be? Well, that's my question. So once again, my f of x is 2x squared plus 2x plus 1. But with Z5, to remind you, Z5 are the equivalence classes 0, 1, 2, 3, and 4. 5 of them. You stop with n minus 1 there. And I'm going to plug these numbers into my function. F of 0, f of 1, f of 2, f of 3, and while I'm at it, over here, f of 4, and f of 5. Don't need f of 5, just f of 4 is where I stop at. So Z4, Z5, I stop at 4, 0 through 4. So here we go. Plug in 0. I get 1. Plug in 1. 1 squared times 2 plus 2 times 1 is still 2. 2 plus 2 is 4 plus 1 is 5. You notice I'm getting the same numbers again. Plug in 2, I'm going to get 13. It's the same function plugging in on my calculator, but I got some more choices here. Second, calculate value. When I plug in 3, I get 25. When I plug in 4, I get 41. Okay, but these guys, some of them, are way too big. Remember, I'm in Z5 adjoined X. So with Z5 adjoined X, I got to convert these guys over. Well, 1's equal to 1. However, equivalence class 5 in Z5 is 0. Equivalence class 13 in Z5 is equivalence class 3. Equivalence class 25 in Z5 is actually 0. Equivalence class 41 in Z5 is back to 1. Well, these are my 2 guys. Doesn't matter the fact that I have 2 of them, I have 1 of them. I got some zeros in this thing. Some zeros implies that this thing is reducible. It's going to factor. It'll factor by the famous x minus 1 factor and the x minus 3 factor on this particular guy. So it is reducible, which means that the ring Z mod 5 adjoined x modded out by 2x squared plus 2x plus 1 is a commutative ring with identity. And this is the work to actually show this. So this is going to be a commutative ring with identity because I got a 0. When I didn't get a 0, my f adjoint x modded out by p of x congruence classes end up being a field. So hopefully this is, section 5.3 is not too bad, but the tie-over, which you should be paying attention to, is the relationship of z mod p and how we got fields off that, and f adjoint x modded out by p of x. When p of x is irreducible, that's prime-ish, irreducible, I'm getting the same concepts. I'm getting fields out of it. So hope this has been helpful, and I'll see you on the next video, chapter 6, which will be the last chapter that we have to cover in modern algebra.